Welcome back to Physical Science 101. This is our final lesson of Unit 3 of the Energy Unit, and we just have a few more topics to discuss, and the first of those is power. Power is work done divided by time. You'll notice that so far in the Energy Unit we haven't talked about time at all. Well, now we're going to bring time in. And power is work done, is defined as work done divided by time. So let's think about what that means. It means that when you lift a weight, if you lift a weight a certain distance, then you do a certain amount of work. So if you lift a weight a certain distance, you do a certain amount of work. Now, if you have more power, you can lift that weight, that distance, more quickly. So the time would be smaller. So the same work, less time means more power. And if you have less power, then you would do that same amount of work over a greater time. An example of this is, let's say that you have to jack up a car to change the tire. Well, if you have some kind of hoist, you can just have that hoist attached to that car and lift the car up in very short time. Whereas if you don't have some kind of motor like that to help you, you have to do it yourself. You'll have to get out your jack, and it'll take you more time to do that amount of work. So, same amount of work to lift the car up. The motor has more power, so it can do that work in less time. So same work divided by less time means more power. Whereas for you doing it with your own muscles, you have to do the same amount of work, but a bigger time. So same numerator, bigger denominator gives you a smaller power. So that is the idea of power. Power is how much work you can do in a certain amount of time. And as we, in our shorthand, we would write capital P for power equals capital W for work divided by time. So power is work divided by time. What is the metric unit of power? Well, the metric unit of power actually gets its own name. It's the watt. So 1 watt is a kilogram meter squared per second cubed. Why is that? Well, let's take a look at our definition of power. Power is work done divided by time. Work is a transfer of energy, so work has energy units, or joules, so it'd be joules divided by seconds. So a watt is a joule divided by a second. And if you'll remember, a joule is a kilogram times a meter squared per second squared, and then we divide by another second, so that would give us kilograms meter squared per second cubed. Now another definition of the watt would be a newton times a meter, because remember, a joule is a newton of force applied over a meter, so a newton times a meter is a joule, and then per second. So a watt is a joule per second, a joule of work done per second. It could also be a newton times a meter per second. But if we break it all the way down into kilograms, meters, and seconds, then that would be a kilogram times a meter squared divided by a second cubed. So that is the watt. Okay, let's put our definition of power to work, and I have a question for you. A 60 kilogram student runs up a 5 meter high stairway in a time of 3.92 seconds. How many watts of power did this require? So you'll have to think about how much work the student did climbing the stairway, and then divide that by the time, and you'll get the power. So how much work did the student do? And remember, the work done by the student is the increase in the student's potential energy. So the work that the student did went towards raising the student's potential energy. Okay, so I would like you to work on that, work on answering that question. So pause, and then come back when you're ready to see my work. Okay, let's draw a diagram. Here's our stairway. Here's our student. We have a square student. The mass of the student is 60 kilograms. And the height, the initial height, is equal to 0 meters. And up at the top of the stairs, the height is equal to 5 meters. And we're going to say that the speed does not change. So the student is running up at constant speed. So V is equal to whatever it is. V is equal to something. And at the top, V is equal to the same something. Whatever that is. Whatever it is, it doesn't change. So the student runs up at constant speed. We have the student's mass. We have the change in height. Oh, and the time. And the time that it takes to go up is 3.92 seconds. Okay, so that's everything in the question. Now let's think about the energy situation. The energy situation is the student's potential energy is increasing, while the student's kinetic energy stays the same. So potential energy increases because the student goes up the stairs. Kinetic energy stays the same because the speed doesn't change, whatever it is. So the student has kinetic energy, but the kinetic energy doesn't change. And to make that potential energy go up, we need to add some energy. So that's the work. Okay, so the work is increasing the potential energy, and we can use this to calculate our work. Let's use our energy principle. Our energy principle says energy increase is equal to the work plus the energy decrease. And there's no energy decrease, so I'm just going to put 0. So energy increase is the work plus the energy decrease, which is 0. And the energy increase is the potential energy. So the potential energy is what's increasing, and that's equal to our work. Our potential energy is mg height. That's the work done. The mass is 60 kilograms. G is 9.81 newtons per kilogram. And the height is 5 meters. That's the work done. Okay, so let's calculate that. 60 times 9.81 times 5. Okay, and that's 2,943 watts. We have kilograms, our kilograms cancel out, and we have newtons times meters. That's a joule, so 2,943 joules is the work done. Okay, so 2,943 joules of work was done. That is independent of how fast the student got up the stairs. The student could have gotten up slowly or quickly, and it would be the same amount of work. But the question actually asked us, how much power did this require? So remember that power is work over time. And in this case, that would be 2,943 joules of work divided by 3.92 seconds. And so the power is 2,943 divided by 3.92, and that would be 751 watts of power. So the student can put out 751 watts of power. If the student could put out more power, then the student could reduce this denominator. If we were to make this denominator smaller, then that would increase the power required. So the faster the student goes up, the bigger this number would be. If the student could not put out that much power, then this denominator would get bigger. It would take more time to go up. And so that would be less power. So that is the idea of power. Power is the amount of work done, which is independent of power. So the work is the same, but power tells us how quickly you can do that work. More power means less time. Okay, here's another power question. How many seconds will it take a 20 horsepower motor to lift a 2,000-pound elevator a distance of 20 feet? Now, obviously, I gave you the measurements here, not in metric units, but in customary English units. So I expect you to do some unit conversions to answer this question. Horsepower is the unit of power, so we would have to convert horsepower to watts, and the conversion factor is 1 horsepower equals 746 watts. So 1 horsepower is 746 watts. 1 pound is 4.46 newtons. So 1 pound of weight is 4.46 newtons of weight. And 1 foot is 0.305 meters. And so that's all the conversion factors you need to answer this question. So first, you have to do your unit conversions. Then you'll have to figure out how much work was done. And then you will use that work and the power to calculate the time. So please do that. Please try and pause and then come back when you're ready. Okay, here's our elevator. It goes up, and we'll say this is height is equal to 0, and we'll say that its speed is 0 at the bottom. At the top, its height is 20 feet, and we'll say that it comes to rest again. So the elevator starts from rest and stops at rest, but it goes up 20 feet, which we have to convert. So let's go ahead and do that. I have feet and I want meters. So I want meters. I have to divide by feet so that my feet cancel out. And I have 1 foot is 0.305 meters. So you can calculate that. I have power. I have the power. Power is 746 watts. Oh no, power is 20 horsepower. And I want to convert that to watts. So watts in the numerator, horsepower in the denominator, so that my horsepower will cancel out. Horsepower divided by horsepower cancels out. And I have 1 horsepower is 746 watts. Okay, and we can figure that out. And I have the weight, and I'm just gonna write, let's see, I'm gonna write mg for weight. I don't want to use W because we're gonna use W for work. So mg is the weight, and we know that the weight is 2,000 pounds. Okay, 2,000 pounds, which we're going to convert to our metric unit of weight, which is the newton. So I want a newton on the top and a pound on the bottom. And 1 pound is 4.46 newtons. Okay, we can calculate what those are. So horsepower cancels out here, feet cancel out here, pounds cancel out there. So let's go ahead and do those conversions. 2,000 times 4.46. The number is 8,920. And newtons, that's our weight, that's our mg. The height is 20 times 0.305. That would be 6.10. And this is a comma. Let me make that a little more obvious. And this is a decimal point, 6.10 meters. And the power is 20 times 746. That's 14,920, comma, 920, 14,920 watts of power. Okay, so that's all, a lot of watts of power. Okay, so now we've gotten everything from our question statement, and actually we have not. There we go. We want to know the time. So now we've gotten everything there. Let's look at the energy. The energy situation is just like we had last time. The potential energy increases, kinetic energy stays the same because it started at rest and it ended at rest. And so there must have been some work done. Okay? Our energy principle, energy increase, equals the work done plus the energy decrease, but there's nothing that's decreasing, so once again I'm just going to put 0. Our energy increase is our potential energy. That's equal to the work done. Potential energy is mgh. That's the work done. All right, mg is 8,920 newtons. That's our weight. And the height is 6.10 meters. That's our work. So what is the work? 8,920 times 6.1 is 54,000, and I'm going to round off here, 54,400. So I've rounded off here. Newtons times meters are joules of work. So the elevator, or the motor for the elevator, did 54,400 joules of work. That almost gets us to our answer. That's the work. We want to know the time. Well, whenever you're dealing with energy and you want to know time, that's power. So that's the only time that we talk about time is when we're talking in the energy unit, is when we're talking about power. So power is the work done over the time. Now I want to solve for time, so I need time in the numerator. So I'm going to multiply by time. And then I want to get this p to the other side. So I'm going to divide by p over here, divide by p over here. These p's cancel out, these times cancel out, and I have time is work done divided by power. And so now you can even see even more clearly that the bigger the power is, the less the time is. The bigger this denominator is, the smaller the whole fraction is. Okay, so the time is the work, 54,400 joules divided by the power, which is 14,920 watts. And I'm going to write the watts as joules per second. And you can see that my joules cancel out. And so the time, and we'll talk about what happens with those seconds. Let's get the numbers. 54,400 divided by 14,920. 54,400 1,400 divided by 14,920, and I get 3.65 seconds. Actually, I get 3.65, and what are my units? Well, I have seconds. I have 1 over seconds in the denominator, so I flip that over to bring it to the numerator. So 1 over seconds, when I bring it to the numerator, becomes seconds. So that is the answer to the question. That elevator would take 3.6 seconds to rise up that distance, given that 20 horsepower motor. Okay, let's talk about another energy concept, and that is the concept of internal energy. So far we've had mechanical energy. Mechanical energy is kinetic energy or potential energy. We're going to introduce now internal energy. And the idea behind internal energy is that an object cannot exert a force on itself to change its own momentum. So think about when I was standing on the skateboard, and trying to change my momentum, change the momentum of the skateboard of myself. I was trying to go forward. Well, I could not do that unless I pushed on another object, or another object, actually, unless another object pushed on me, because I pushed on the board and the board pushed back on me, or I pushed on the ground and the ground pushed back on me. So an object cannot exert a force on itself to change its own momentum. Something else has to push on an object to make it change its momentum. However, an object can do work on itself. So we can have an object do work on itself. An object cannot change its own momentum, but an object can change its own energy. And since that energy has to come from somewhere, it has to come from inside of that object. So if an object does work on itself to change its kinetic energy or its potential energy, then there must be a corresponding decrease in internal energy. Now let me do a demonstration to show you what I'm talking about. Okay, here we are with one more demonstration with the skateboard. This time we're going to talk about work and energy. Okay, so once again, I will push off of the ground, and I will start moving, which means that I will gain kinetic energy. So as I push off and start moving, I go from having 0 kinetic energy now to having some positive amount of kinetic energy. Therefore, something did work on me. Something did work to give me kinetic energy. So here we go. I'll push off, and I go from having no kinetic energy to having some kinetic energy. Okay, now let's think about what it is that did work on me to give me my kinetic energy. Now, when we were talking about momentum, we made a big deal about my foot on the ground, saying that I pushed off, but it was the ground that pushed on me to accelerate me forwards, to give me my forward momentum. Now let's think about that. Let's focus in on my foot. Okay, I'll even stand on my toes so that I have a smaller footprint on the ground. As I push off on the ground is exerting a forward force on me, but there's no distance. So watch my foot as I push off. Okay, so as I pushed off, the ground exerted a force on me. That's what gave me my momentum, but that force was applied over 0 distance. So force times 0 distance means 0 work. So the ground did no work on me. Well, where did my energy come from if the ground didn't do any work on me? This time, let's think about my hip, okay? As I push off, my hip is pushing on the rest of my body. So think about all my body except for my leg. My hip is pushing my body forwards, and my hip is going over a distance. So my hip is doing work on me, definitely. So I'm going to push off, my hip's pushing. So my hip exerted a force on the rest of my body, so my hip did work on the rest of my body. Well, okay, let's think about that. We have my foot on the ground where no work is done. We have my hip pushing on me, work is done. So the energy must have come from somewhere between the floor and the hip. And what kind of energy was that? Well, it is the chemical energy in my leg that is being converted into work at my hip, which is being converted into kinetic energy for the rest of my body. So it is actually my leg that is providing the energy that gets turned into chemical energy. So that's internal energy. That is actually internal to me and the skateboard. My energy doesn't come from the earth. Even though the earth exerts a force that gives me my momentum, my energy comes from chemical energy in my leg being converted into work at my hip, being converted into kinetic energy of my whole body. Okay? So here we have a case of internal energy, work being done by an internal energy conversion. Chemical energy in my leg being converted internally into work, being converted into kinetic energy. Okay, so here we go. I have no kinetic energy now. Chemical energy in my leg is being converted into kinetic energy in my body. So once again, that is an example of internal energy, chemical energy in my leg, being converted internally into work, being converted into mechanical energy, kinetic energy in this case. You would have the same thing if you walked up a flight of stairs, except in that case, you'd be converting internal energy into potential energy, for example. So this is one example of internal energy conversion into mechanical energy. Okay, so as you can see, the force that made me go forward was from the ground pushing on my foot. However, the work that made me go forward came from inside of my legs, and also the energy that got turned into kinetic energy as I went forward came from inside of me, came from my legs, so from some form of internal energy. In this case, it's chemical energy. I have chemical energy in my leg, and that is what I use to transform into kinetic energy. Okay, let's do an energy diagram of that. We have our box of energy. That box represents an object. And we still have our mechanical energy, meaning our kinetic and our potential energy. But I also have two smaller boxes inside of our box. We have a box of internal energy, which could be chemical energy, for example. And we can convert that chemical energy into mechanical energy. That would be internal work, and that would be the arrow pointing from internal energy into work. So I can decrease chemical energy, and that energy decrease in chemical energy becomes transferred through the work into mechanical energy. So a single object can decrease its chemical energy and increase its mechanical energy. Might be kinetic energy, as when I was pushing off on the skateboard. Might be potential energy if I were climbing up some stairs. Okay, so we still have our box of mechanical energy. We have a box of internal energy. And I'm also going to introduce another box, which is thermal energy. That's the energy of a warm object. Okay, and that is going to be the topic of the next unit, of Unit 4. We're going to spend a lot of time talking about thermal energy. As I said, energy is going to carry out through most of the rest, if not all of the rest of this course. Energy is a very big idea that is going to carry through all the rest of this course. So let's look at our box. We have our mechanical energy, which is our kinetic energy and our potential energy. We have our internal energy, chemical energy, and we have thermal energy. And why did I put thermal energy there? Well, our conversion of internal energy into mechanical energy is not very efficient. Okay? If we were to reduce our chemical energy by a certain amount, meaning when our muscles work, when our muscles convert chemical energy into mechanical energy, they do work. So some of that energy is converted into work, but a lot of it goes into thermal energy. That's why we are warm objects. We're warm objects because our body is continually converting chemical energy into thermal energy while it's doing work. So let's take a look at our energy principle. Our energy principle is the same, okay? Mechanical energy increases equal the work done plus the mechanical energy decreases. And in this case, the work comes from inside of the object, comes from a conversion of internal energy into mechanical energy. So decreasing chemical energy is transformed into mechanical energy through internal work, but at the same time, a lot of that chemical energy is converted into thermal energy. So the decrease in chemical energy equals the work done plus the heat. And then efficiency would be defined as the work done divided by the decrease in chemical energy. And so that's always going to be a number less than 100%. Okay? So if we decrease, let's say, 100 joules of chemical energy, realistically, we'll probably only get 20 joules of work out of that. So a decrease in chemical energy of 100 joules can give us 20 joules of work and 80 joules of thermal energy. So that would actually be an efficiency of 20%. So 20 joules of work divided by 100 joules of chemical energy, that would be an efficiency of 20%. So this brings us to our idea of conservation of energy, which is one of those big ideas. The big idea of conservation of energy is that energy can change form, but it is never created or destroyed. It's conserved because the amount of energy never changes. 100 joules of chemical energy can be turned into 20 joules of kinetic energy plus 80 joules of thermal energy. So the total is the same. We have a decrease of 100 joules of one kind of energy and an increase of 100 joules of other kinds of energy. So energy can change form, but it is never created or destroyed. And so we call that conservation of energy because the energy is conserved. 100 joules of energy stays as 100 joules of energy even if it changes form. Now, energy can also be exchanged between objects. If I were to do work on an object, then I would lose that energy and that object would gain that energy. So we can exchange energy. And if we can exchange it, then that is something that's worth money. So energy is money. Okay, here's some numbers. Let's start with natural gas. I looked at my gas bill, and my gas bill was $3.50 per 1,000 cubic feet. Okay, so I would buy 1,000 cubic feet of gas, and the gas company would charge me $3.50 for that. Well, I use that gas to heat, and that is a very efficient process. I can turn almost all of that, all of the energy into heat, and so if I calculate how much heat I can get out of 1,000 cubic feet of gas, then what I can work out of that is that for every $1 that I send to the gas company, they give me 285 megajoules, 285 million joules of energy in the form of heat. So I am giving the gas company my money, and they're giving me energy. And for every dollar that I give to them, they're giving me 285 megajoules of heat. So when you pay the gas company, you're buying that energy in the form of stored in the form of gas, chemical energy. So it's they're giving you chemical energy, which you then burn and turn into heat. So you're paying them for the chemical energy in that natural gas. Now, how about electricity? Once again, I looked at my bill, and my bill said that for every kilowatt hour of energy that I got from the electric company, I had to pay them 10 cents. So if I convert a kilowatt hour into joules, then I can work out that for every dollar that I pay to the electric company, I get 38 megajoules of electrical energy, which I can use to drive motors. I can do a lot of things with it. I can turn my TV on. I can do a lot of things with that energy. So for every dollar that I pay to the electrical company gives me 38 million joules of energy, of electrical energy. So you might ask, well, why does the electric company only give me 38 million joules of energy for my dollar, whereas the gas company gives me 285 million joules of energy? Well, the first thing is, if we think about it, how does the electric company generate its electricity? A lot of times they burn natural gas, okay? So they have to buy natural gas, and then they burn it, and that is very inefficient, okay? To convert, they can convert the natural gas into thermal energy very easily, but to convert thermal energy into electricity is very inefficient. So they have a lot of losses just from that conversion of the chemical energy in the natural gas to electrical energy. They get about 20% out. So they lose 80% of the energy into thermal energy when they burn the gas. So when they burn that gas, about 80% goes into heat and about 20% goes into electricity. So the 285 million joules of chemical energy that they get in the form of gas can only generate a much smaller number smaller number of million joules of electricity. So they can only give me less. They can give me less electrical energy than the amount of chemical energy that they buy. So that cuts down that number a whole lot, from 285 million joules of chemical energy in the gas to about 38 million joules of electrical energy that they have to sell. And there's also overhead. They have to run the plant. They have to transport the electricity. So there's a lot of overhead there. So that cuts down on the amount of energy that they can give me for my dollar. When it's all said and done, I can get about 36 million joules of electrical energy for my $1 that I pay them, the electric company. Okay, let's talk about gasoline. When you go to the gas station, what you are buying chemical energy from the gas station. You're giving them money. They're giving you chemical energy in the form of gasoline. And how much do you get? My number here, when I worked out these numbers, gas cost about $2.50 a gallon. That might be a little dated by now, but you get the idea. Okay, to buy a gallon of gasoline, at the time, I paid $2.50. And if we assume about 20% efficiency in converting that chemical energy into kinetic energy in my car, then my $1 that I buy in gasoline gives me about 10 million joules of energy. So you can see right there why there is a benefit in terms of energy to having an electric car. Okay? For your $1 of gasoline, you're going to get about 10 million joules of work out of your car. Whereas if you were to fill up your car, if you had an electric car and you filled up your car's battery from the electric company, you would actually get almost 4 times as much energy, about 36 million joules for your dollar. So you can fill up your car's batteries with energy for a lot more cheaply than you can fill up your car with chemical energy in the form of gasoline. Okay, let's talk about food. I thought about what's the cheapest kind of food I can buy, and I thought, well, I can buy some oil and some flour, get some water. I can make some kind of a cracker or tortilla out of that. I can make some kind of bread out of that, and I looked for some canola oil. I got $1 would buy me 24 ounces of canola oil. Flour, $1 would buy me about a pound of flour. And if I look at the calories in the food and convert that to joules, and assume about a 25% efficiency in converting food into energy, then my $1 of food will give me about 3.8 million joules of energy. So less than the gasoline, but we can't drink gasoline, okay? So the gasoline gives us more energy per dollar, but we can't drink it. We can't get our energy that way. So food costs a little bit more, or we get fewer joules, fewer million joules of energy out of food because it's more refined. It has to be the kind of food that we can metabolize. It has to be, we can't just have any chemicals. We have to be particular about the chemicals that we put in our body. And to get the kind of chemicals that we can put in our body costs more money, or in other words, we get fewer joules or fewer megajoules for our dollar. Okay, now this one is interesting. If we look at electricity from a battery, from a non-rechargeable battery, I paid about $20 for 48 AA batteries. And if I work out the amount of chemical energy that can be converted into electrical energy in a AA battery, my $1 there bought me about 4/100ths of a megajoule, 0.04 million joules of energy. So what does that mean? That means that when I buy a battery, I'm buying the chemical energy in that battery, and for my $1, I'm getting 4/100ths of a million joules. How could I do better than that? Well, I could buy rechargeable batteries. And if I were to buy rechargeable batteries, then I could refill them with energy from the electrical company. And the electrical company will give me about 36 million joules of energy for my dollar. So that's about 1,000 times more. So the energy that goes into batteries is about 1,000 times cheaper when you recharge a rechargeable battery than when you buy a disposable battery. So when you pay for your natural gas, when you go to the gas station, when you buy electricity from the electrical company, what you're buying from them, what you're exchanging your money for, is the energy that they give you in one form or another. So, natural gas, gasoline, these are all convenient forms of energy. They're very, very dense forms of energy that can be exchanged very easily between people in exchange for money. But where does that energy ultimately come from? There are really only two ultimate sources of energy on the earth, and those are sunlight and nuclear energy. And sunlight is the only renewable one. Sunlight, we get energy, we get radiant energy from the sun. We get a lot of radiant energy from the sun. In fact, the radiant energy that we get from the sun is more than 10,000 times the amount of energy that we use in a day. So the radiant energy that we get from the sun in a day is 10,000 times what the whole world uses. So we get a lot of energy from the sun every day. So the sun is constantly putting out energy that we can use. Gasoline, natural gas, those are really stored energy. So those are storage of energy, of sunlight, that the sunlight has shined on the earth millions of years ago. And the plants absorbed it and converted that radiant energy into chemical energy. And then when the plants were buried, they underwent some chemical processes to form very compact, very dense energy stores. So all of that energy, when you drive your car or when you burn gas to heat your house, all of that energy ultimately came from the sun just a long time ago, okay? Our income is from the sun. You can think of gasoline, oil, natural gas. All of those are really our savings account, okay? The sunlight fell on the earth long ago, and some of it went into our savings account. And our savings account of energy are these fossil fuels. So we can take out of our savings, and right now we're taking out of our savings a lot faster than we're putting into our savings. So right now we're living on our savings, but if we want to be sustainable, we will ultimately have to use that sunlight that comes from the earth, because that is really the only renewable source of energy on the earth. Now, there is also nuclear energy. Nuclear energy is something we'll talk about in Unit 7, in the last unit. We'll talk about where nuclear energy comes from. The earth has some nuclear energy, and it can last for quite a while. We can use nuclear energy we could power the whole earth with nuclear energy for a couple hundred years, but it's not a renewable source. So we do have to be careful with that one as well. It is also a savings account. And you might ask, what about geothermal energy? Interestingly, geothermal energy is mostly nuclear energy. The earth would have frozen solid without radioactivity going on inside of the earth. It would have frozen solid long ago. So the only thing that keeps the earth from freezing solid right now is our natural nuclear reactions going on inside of the earth. So our only real two sources of energy are sunlight and nuclear energy. A lot of the rest are just stored sunlight. And geothermal is actually nuclear energy stored in the form of thermal energy. So those are really our only sources of energy here on Earth. Okay, here's one question on the topic of conservation of energy, and that is, in all of our energy uses, we find that A, the energy used is consumed, B, some forms of energy are consumed but not others, C, more energy is created than is consumed, or D, the total amount of energy is constant in all situations. So as always, definitely come down on an answer. It's important that you convince yourself of one of these answers, and so that when I tell you the answer, you'll know if you got it right or if you have something to learn. Okay, the correct answer here is D. The total amount of energy is constant in all situations. That is what we mean by conservation of energy. It means that energy can change forms. It can change forms from chemical energy to thermal energy, for example, or chemical energy into kinetic energy. But if you have a decrease of 100 joules of chemical energy, you have to have an increase in 100 joules of other forms of energy. So the total amount of energy in all of its forms is constant in all situations. Okay, final thing. We introduced the energy principle in this unit, and we introduced the momentum principle in the last unit, and I said that these were powerful ideas that scientists use to describe things. I'm going to show you here how those two things relate to each other. How do energy and momentum relate to each other to describe a particular situation? Okay, we're going to go back to the 0.015 kilogram bullet that is fired with a velocity of 2 meters per second from a 6 kilogram rifle. What is the recoil speed of the rifle? That's a question that I asked you last time. That is conservation of momentum. Remember that mass times velocity in one direction equals mass times velocity in the other direction. So you use momentum ideas to answer that question. But then I would like you to work out what is the kinetic energy of the rifle and the kinetic energy of the bullet. So the rifle and the bullet will have equal amounts of momentum, but you should find out that they have different amounts of kinetic energy. And then finally, how much force is necessary to stop the rifle in 0.1 meters, and how much force is necessary to stop the bullet in 0.1 meters. And there we'll see the difference between energy and momentum, okay? Because you'll think about work, and work is force times distance. So, and it takes work to stop the bullet and the rifle. Okay, there's my rifle, there's my bullet, mass of the bullet, mass of the rifle, speed of the bullet, speed of the rifle. The speed of the rifle is what we want to know. Mass of the rifle is 6 kilograms. Mass of the bullet is 0.015 kilograms. And the speed of the bullet is 200 meters per second. Okay, now we want to know the speed of the rifle, and that is conservation momentum. The momentum of the bullet and the momentum of the rifle are the same thing. So mass of the rifle, speed of the rifle equals mass of the bullet times the speed of the bullet. And I want to get speed of the rifle, so I'm going to divide by mass of the rifle on both sides. That cancels out mass of the rifle over here. And the speed of the rifle is equal to the mass of the bullet, 0.015 kilograms over 6 kilograms times 200 meters per second. And I'll just work that over there. And what is the speed of the rifle? 0.015 times 6, divided by 6, 0.015 divided by 6 times 200 is 0.5 meters per second, because my kilograms cancel out and I'm just left with meters per second. So the momentum of the rifle and the momentum of the bullet are the same. What about energy? So the kinetic energy of the rifle is 1/2 mass of the rifle, v rifle squared. And the kinetic energy of the bullet is 1/2 mass of the bullet, speed of the bullet squared. Okay, so that would be 1/2 times the mass of the rifle, which is 6 kilograms, times the speed of the rifle, 0.5 meters per second squared. And the kinetic energy of the bullet would be 1/2 mass of the bullet, 0.015 kilograms, times 200 meters per second squared. Alrighty, and what are those? 1/2 times 6 times 1/2 squared is 0.75 joules of kinetic energy for the rifle, and 1/2 times 0.015 times 200 squared, that would be 300 joules of kinetic energy for the bullet. So what you see here is that while the rifle and the bullet have the same momentum, the bullet has many times more kinetic energy. And this is going to be really important later on when we talk about nuclear reactions as well. So that's the interplay between momentum and energy. The rifle and the bullet have the same momentum, but the bullet has most of the kinetic energy, has many, many times more kinetic energy. So when the rifle was fired and and chemical energy was converted into kinetic energy, the bullet got most of the kinetic energy. Okay, so the bullet has a lot more kinetic energy. And I should have put KE there, but so kinetic energy and kinetic energy. Okay, so let's answer that last question. How much force is necessary to stop the rifle in 10 meters? Well, we know that the work is equal to the change in kinetic energy. So the work to stop the rifle would be the force to stop the rifle times the distance. That would be the kinetic energy of the rifle. And that would be, so if we want force, we'll divide by D. So the force to stop the rifle, cancel out my D's, would be 0.75 joules divided by 0.1 meters to stop the rifle. So 0.75 divided by 0.1. Nope, I did not do that right. Divided by 0.1 would be 7.5 newtons of force to stop the rifle. So to stop the recoiling rifle in 0.1 meters only takes 7.5 newtons of force. The force to stop the bullet in that same distance, force to stop the bullet would be 300 joules divided by 0.1 meters. And that would be 3,000 newtons. Okay, so to stop the rifle in to stop the recoiling rifle in 1/10 of a meter would take just 7.5 newtons of force. To stop the bullet over the same distance would take 3,000 newtons of force. So that's why the bullet does more damage and when it hits something than the rifle does to the person firing it. So that's just an example of the interplay between energy and momentum. And as I said, I'm going to come back to that when we talk about nuclear physics in the last unit. Okay, that is the end of the energy unit. When we come back next time, it'll be to talk about thermal energy. So back on energy, but in this case, thermal energy. So thermal energy next time, and until then, think science.